I want to talk today about interpreting graphs and trends in graphs and things like that. So a big part of this course is going to be like, hey, you've spent 3 years in high school learning kind of different types of math. In grade 9, you spent a lot of time on linear relationships, right? In grade 10, you spent some more time on lines, but then you also started to talk about parabolas, right? And then whether you remember or not, in grade 11, you started to deal with exponential functions, right? Where the x is up in the exponent, we got a different kind of graph. And now in this course, we're actually not going to add a new type. But what we are going to do is start to look and say, with all 3 of those, how do we use those in real-world applications? How do we pick between them and things like that? So before we do anything, I want to say, in math and science, why do we graph things? Like, what does it mean when we graph something in math and science? Something like this. Like, we're going to look at an example here. This is real numbers, by the way, because I know somebody who works at an ice cream shop at a beach. And so I asked for some numbers. Because rather than spend 10 minutes planning a lesson that should only take 10 minutes, I like to spend way too much time. Yeah, so what do you think?
Kind of like an overall view of how two factors relate to how they end up on them.
Good, good. This is all about relationships. You know, yesterday was Valentine's Day, so this is a good time to talk about relationships. Graphing is all about relationships. Also, if you make graphs for people you love, they'll appreciate it. Everyone loves graphs. It's the thought. You could put like, you could do something like this, right? You could say like, dear person I love. Right? And you could say like, look at this. Isn't that romantic? Right? And then the person whom you love will be like, thank you so much. That was so sweet, person who loves me. This, yes, yeah, this is, and like that neatly too. Just kind of scrawl it on there. She's like, oh, Mr. Orlando, because that's what she calls me, of course. You're so romantic. And I said, yes, Mrs. Orlando, I am. I don't think I've ever referred to my wife as Mrs. Orlando before. I was really weird. I did not care for that. Anyway, yeah, it's all about relationships. So when we take information and we graph it, the idea is to measure 2 sets of information and see if there's something that relates them. And you can do that with anything, right? So in grade 9, you probably have to stand there and measure your arm. Did you guys do this? You measure how wide your arms are and measure how tall you are? Everyone do that? Yeah, right? And then you take everyone's data and you put it on a graph and you see like, taller people have longer arms and shorter people have shorter arms, right? Do you do that example? Or maybe shoe size, they do that one where they like measure how tall you are and then measure how big your foot is. Some variation on that. And these things are pretty intuitive, right? So what I want you to do is just take a minute and just graph this data. And I already set up the scale for you. I think they all fit. I hope they all fit. Did I set the scale well? That's the question. There's one that doesn't fit. That's okay. We can kind of expand. I think there's one that's 25 point something. Yeah. So there you go. So take a minute and graph that. Whilst you do that, I'm going to freeze the screen, and I'm going to do it too. Hi, how are you? I'm well, thanks. What can I do for you? No, don't be, please.
I just wanted to know, we're working on the co-op. And they already have someone leader. There's no one at Maine last year texting me. Just me. So, do you think that's coming right away? If you guys finished 5 minutes later?
Oh yeah, she can go as early as she needs to. No worries. Mhm.
Bring up the question forward.
No, we're just going to talk.
Okay.
We're just going to talk. Unlike last time around, that's not like my primary focus this time. Do you? Oh, I'm sorry. Yeah, no, it's true. You have to like just do your best. That's what I came up with. And I used my rainbow pen because my rainbow pen makes me happy. Right. I find helpful across the numbers like those. Otherwise, I lose track. By the way, we're not going to do a lot of graphing by hand. We're going to do like the note because, yeah. Then you have to worry about them being not on the left. Exactly where they should go. But it's good to remember that, you know, one time in the world we had to do these things by hand. Right? Okay, so maybe you're still finishing up here, but let me ask you. Looking at this, what's your sense? Yeah, right, that would be a reasonable interpretation. We think in general, hotter weather equals more ice cream. I want to mention something. Do you think more ice cream means hotter weather? Like, do you think if I have a really busy day and lots of people come and buy ice cream, that causes the planet to cool that one particular day? Right, that's silly, right? I mean, that particular example sounds goofy, right? But I want to mention this because it's kind of a rule of thumb in science, where down here we put what we control, and I'm going to put control in kind of quotation marks because it's not always something we're in control of or what we measure, the thing we're looking at, the thing we're interested in, and up here we always put the outcome. And that's a rule for science. And it's not that there's something magical about going up and down versus left and right, but rather somewhere along the line, somebody said, if we all do this the same way, then we can just quickly look at a graph and know what we're looking at. Does that make sense? So in this case, when we say like what we control, obviously we don't control the weather, but what we're saying is that the weather is in control of our sails, not that our sails are in control of the weather. Does that make sense? Right? And the science-y term for that is we call this one the independent variable. In other words, the weather is independent of us. Sorry? I know. Right? Look at me. And we're going to use it. We're going to talk about it. And we call this the dependent variable because it depends on. Oh, be quiet. All right. On the next page, I've got another set of data. And actually, I think I said last year on it. That's like 2 years ago. But this is real data. It's a class I taught. I should put the names in there. But anyway, and so here we're comparing what? What are we comparing here? What are we comparing? Good. So what are we thinking is the outcome? What should we be putting on the up and down? Yeah, I like that, I think. I'm thinking probably mark as a percentage here. And then what would we put down here? Yeah. All right, so give that a try. See what you get. What do you think? Sure, as a rule. Like now, does that mean everyone will be like that?
Some people can miss grades if they want on school.
Yeah, and some people are just super keen, right? Like some people are like they're like super clever, and it's like they can miss tons. But most people aren't like most people have to attend to do well. And some people, you know, struggle with a class, and even if they attend every day, they're still not going to get a 99, right? There's nothing wrong with that. But this is a general guideline. Now, yeah. Yeah, that's right. They attend because they want to go to foods class or, I don't know, science class. I'd rather be in science class than I love math. Really love science. All right, so I'm going to freeze one up here, and you guys can give that a try. Yeah. It's good practice for you. Well, like, Sarah drives me nuts, but I can't kick her out of class, right? Like, you got to do it. I'm just kidding. Eventually, I'm going to kick her out of class. That's true. That's true. But that's okay. That's what I got. If your scale's a little different, then maybe you went all the way down to 0, then it'll look crunched up relative to that. But that's the basic trend. No, now is it a perfectly clear trend? No, like this guy missed a bunch of days. He got like an 80 something. That's pretty much. And this poor guy, and didn't miss a single day. He did okay, but he didn't like get perfect. And this guy only missed a couple days, and he had a really rough go. I know that. He's super nice kid. I love that.
Oh, these are actual marks.
Oh yeah, that's real. Why work with fake numbers when you can work with real numbers?
So 2 people, this
Yeah. Nothing. I'll take a last semester.
showed up every day.
Yeah. Wow. They said perfect attendance when I was in high school. This was 2 years ago. This is actually in Smithville. But I wonder. Did you? I don't think you did. Did you? No. Yeah, some kids still have perfect attendance. Especially like certain things make people miss, right? Like if you sickness or vacation, or if you're on like sports teams, they tend to be during class. But not all of them. Some sports are always after school. Okay, again, what would you say the trend is here? In general, what would you say? Yeah. Miss more, lower grade. Now, this one's interesting to me because the cause could go both ways. This. Might you miss more class if you have a bad mark? There's an argument to be made, right? Man, I'm doing really crappy in science. Forget it. Who cares, right? Yeah, or, man, I'm doing great in science. I better attend every day because I want to keep doing that well. So in this case, you can actually make the argument for putting that graph both ways, I think, right? Which is an interesting discussion. You could argue that these both have effects in both directions. Yeah, missing might lower your grade because you're going to not see everything. You're going to miss information. But on the other hand, having a terrible grade might affect how much you go. Having a great grade might affect how much you go. right? So I think this is an interesting case. That's what I like about real numbers, right? Is that they get interesting, right? We can have debates, we can have discussions about what they mean. We think of math as this thing that has like fixed, real, meaningful answers, right? But often when we get numbers from the real world, that's just step one. And then step two is, what does this mean? And a lot of really bright people will say totally different things. You'll have two scientists who look at the exact same set of data, and one will say, this is true, and the other person will say, no, this is true. And then you make them leg wrestle. Whoever wins the leg wrestle, that's who is right. That's just how you do it. That's science. Everyone knows that leg wrestling proves that you're correct. Just if you're wondering, next time you're having a disagreement with like your friend or sibling, just say, all right, this comes down to a good old-fashioned leg wrestle. Okay, so now I already made the graphs for you. But once we have a graph like this, so this is back to the temperature and ice cream cell. So if you go to your next page, I already graphed it for you. And the question is, once you have that information in a graph, what can you do with it?
Analyze it.
You can analyze it. And what's one of the first ways we analyze information in a graph? I can't imagine what I want you to do. What do you think? Yeah, so we could look at this and we could say, this has a trend. And how could I demonstrate the trend that this particular information, the trend that this particular information has? What does this trend kind of look like? Yeah, this one works really well with a line of best fit. So I could take my ruler, and does anyone remember what the basic rule of thumb for a line of best fit is? Yeah, we try as a rule of thumb to have as many points above as below. It's actually a little bit trickier than that, where the real idea is to have as much distance above as below. That makes sense? But I'm going to say this looks okay. I'm going to draw my line of best fit there. Likely you can do better, and I encourage you to do so. But I would say I have 1, 2, 3, 4, 5 points below, 1, 2, 3, 4, 5, 6, 7 points above, but my points below are further away. So I think I like that as a line of best fit. I mean, like that one's pretty far from the line. That's pretty far from the line. Yeah, but I want you to extend it. I want you to extend it. We're going to talk about that. Once I have a line like this, what can I do with it? Why, other than just giving teachers something to do we say, hey, put a line through your points? What might be the reason for that? What do you think? What do you think? I want you to know, and this is true, that last night I tried to look for data related to watermelons because I was going to be really impressive and topical, and I couldn't find it. Nothing came to mind. But I tried. I made a valiant effort, and then I gave it.
Wait, did Alexis tell you that
Yes.
it was one of
She did. So, why put a line through this? What's the point of that? Because now, like if you look, this is kind of a dead space in there, isn't it? Like in this one little area here, we don't have any data, right? And like in this area here, there's no data. So I don't necessarily know, like I have no data at 20. So I don't know what a 20-degree day looks like because I never had a 20-degree day. But with this line, what can I do? I can say, hey, if it were a 20-degree day, what would I expect to happen? And the way we do that is we would just say, okay, let's say, I don't know, give me a number we want to make a prediction about. What kind of day are we interested in? What do you think? Anybody? 23, okay, so let's say, and that's what, roughly there maybe? And so we could say, hey, on a typical 23-degree day, what would I expect to sell in ice cream? By the way, if anyone of you works in like a restaurant or a shop or something like that, your bosses do this every day if they're good at what they do with all kinds of factors. You know, I used to look at a sports bar. So we had a patio. We looked at what's the weather going to be like, because that made a difference. Is it going to rain? That made a difference. Is there a big sporting event on? That made a difference. And we had all these models that we built, so that what day of the week is it? So that we could make a reasonable prediction. Yeah, but even if they're just guessing, even then, they're not just guessing. They've done something like this in their head, right? It's not as formal as this, but they've started to understand the relationship between things and how much they sell.
So it's just like, oh, it's a holiday. Okay, we're gonna get more people. It's a weekend. We're gonna get more people.
Yeah, and that really is this. It's just not as formal as this. And so we would expect on a 23-degree day to sell roughly how much? Well, what's that, like a little over 500? Almost, well, maybe just 500 spot on, right? So I'd say, yeah, on a 23-degree day, I'd expect to sell $500. Hey, if my sales are 100, how hot do I think it was? What could I do? What could you do? If you wanted to know if I sold $100, what was the weather like? What could you do? Love it. Good. Let's see it. Oh, yeah, we're all going to have slightly different lines because we all used our own best judgment, right? Use your line, not mine. Who am I? I'm just a guy in a coffee-stained shirt. Come on. Yeah, yeah, sure. Nine's as good a read on that as anything. Absolutely. But you have to make some interpretation, right? So based on my line of best fit, and we're all going to have slightly different answers, and that's okay. I would say mine looks like maybe a what? 6 or 7? I'm going to say 6.5. That 6.5 degrees Celsius would be about $100. And again, we're doing this on kind of an ad hoc basis. So my guess would be about 6 or 7 degrees Celsius. That makes sense? Now, based on this graph, what temperature would I expect just my little beach place that sells ice cream to just stop selling ice cream altogether? Nobody's going to show up.
Well, yours probably about 1 or 2.
Yeah, I would say that's probably about 2, don't you think?
On mine, it's 6.
Sure, well, then put for yours. Does that make sense? It's when it bottoms out. And by the way, yeah, if you own a little ice cream shop on the beach and all of a sudden in the middle of summer it was 2 degrees Celsius, people probably aren't like, get me some ice Haagen-Dazs.
Actually, I get ice cream every winter. That's when I mostly want ice cream.
Sure, but not like walking around outside, right? You get it and then you eat it at home, I'd imagine. Well, you're the exception to the rule.
I also don't know what
You're like the one data point on here that's like, what happened here?
I'm probably at like,
Actually, I just assumed you bought $300 worth of ice cream. That's a lot of ice cream.
I feel like over depends on the
Fair
I
enough.
thought you were going to say it depends on Kendra's mood.
And I want you guys, for now we're going to move on. I want you to come back to these questions after. Okay? I don't want to go through all of them right now together. So come back to these ones later on and try and answer them. And I want to move on to the next example. Because here, this is going to be harder to draw a line of best fit, right? So use your best judgment and draw the best line of best fit you can. In general, should this line be going up like this or down like that? Down. And we want to try to split the difference, and you're going to have to use your best judgment. Later on, I will show you how you can use a computer to use its best judgment and try to build a line of regression. I feel pretty good about that. I don't feel great about it.
I think like my life.
That's okay. Listen, can I say something for the record? Like, you don't have to like everything we do in math class. Like, that's okay. Like, I seem to remember there being days in like French class when I wasn't like, yes, I'm so excited to be doing ER verbs. Like, it's okay. If one day you go to math class and you're like, I don't care for this,
I love math though.
I like math too,
And it
but
helps myself when I don't like it.
fair enough. Now, I just want to draw a distinction here, because this is the kind of things that mathematicians start to argue about, which is this part of our line of best fit is based on data in that range. Does that make sense? What about this part of our line of best fit? Yeah. Now, could it still be predictive? Sure. But we have no evidence for this region. Does that make sense? So there's no evidence for this line versus this part of the line, which is based on evidence. And this is an important distinction, and we're going to talk about it a lot as we go through this course. Could we assume this line will go on forever? Well, at some point that stops making sense, right? We're going to get to some point where it'd be like, your grade should be negative 30. Are you ever going to get a negative 30?
Well,
I mean, Chandler maybe.
just stop asking.
I might give Chandler negative 30. But none of the rest of you. Or I could follow this line all the way down until we had like 500 absences. But can you have 500 absences in a course? No, that doesn't even make sense, right? Or I could follow this line the other way and be like, oh man, if you miss negative 30 days, you should have 200 in this course. Does that make any sense? No, right? So the one thing I want to point out is that when we use a line of best fit, it is generally safer to work in this area where the line is based on data, and we call that interpolation. It's like interpreting, but interpolation. So what we did on the last page, where we made predictions based on our data, that's called interpolation. But then when I asked you to say like, hey, when would you stop selling ice cream completely? That's outside of our data range, right? If we go back to this graph, all of this, oh, I went too far. Oh, I'm so sad. All of this was inside our range, right? And all of this was outside of it. When we ask these questions, that's from the outside. And the opposite of internal is, yeah, what's another word for that? Internal and external. So if this was interpolation, this will be very good. And the way we pronounce it is extrapolation. Maybe you've heard the word extrapolate. So if I use this to say that somebody who misses 15 days should get, according to mine, what score should they get? These are all 10s, right? So 40, I think even like 10, 20, 30, 40. Like even below 40, that would be 40. So maybe like 35. So if I said somebody who missed 15 days should get about 35%, that's an extrapolation. I'm working outside of the data I have. And by the way, like, probably not. Like 15 days is a lot, but it's not so much that you're going to get like 35. I think, yeah. Yeah. Yeah, and listen, absolutely. And that is part of the point of this too, because also, don't forget, some people may miss a huge block of days because they have like a medical issue, but then they like get private tutors and instruction. Like there's all kinds of other things going on. So interpolation and extrapolation. I'm going to have you do these questions on your own later. So we're going to skip them for now. It's okay, I'll tell you. I will remind you. But you really want to listen to me blabber on for like the next hour about every one of those questions? Okay, well, I don't. I don't know about you, but I get sick of the sound of my voice after approximately 1 minute.
Not that I could do those, just go on.
I bet they would. Okay, so I want to talk now about, over the course of your time in math, you've learned about a few different kinds of models. You know how to do linear relations, that's what we just did, right? You learned about quadratics, which, does anyone remember what's the name for the shape of a quadratic? Very good, so those are parabolas. And then you also learned about exponential equations. And like these are ones where you did like, if we start with 200 bacteria and they double and we let them double 13 times, right? So this is where things are doubling and tripling and being multiplied over and over again. Those are exponential equations. And one of the things we're going to do in this course is we're going to start looking at real data, real world data, and trying to use these types of things to model them. So I've got some examples here. And these are also real data. Though we're going to talk about this first one because, interestingly, this is a study of countries that was released by a company that makes, well, let's see if you can guess. This is a graph comparing how much wine they drink on average in a given country. And this is in liters per year. So if you are an average Italian, you are drinking 78 liters of wine in a year. Just to be clear, that's an average of about a quarter of a liter per day, which is a lot. It's not that much. It's like a big glass of wine a day. It's like a good sized glass of wine a day, but still that's not nothing. And up here is mortality. And specifically, this is like years less than, or not, sorry, no, it's weeks or months less than adjusted average. So it's like the change in life expectancy that's not measured in years, it's measured in like months. So they've taken life expectancy and graphed it against how much wine you drink. Now, first of all, let me ask you this. Does a line fit this well? Not very well, right? I mean, it kind of doesn't matter how you draw the line. It's really crappy, right? Like, because now this, like, these are crazy off. So what kind of shape would fit this? Now, the problem with the parabola is it implies we get something like that, right? Do we have any evidence of that here? No. Which makes me think that we have a shape like this. Does anyone remember what shape that is? Yeah, specifically, well, you have three options. Yeah, this would be exponential decay. Exponential growth is a similar curve, but instead of going down like that, it goes up. So that would be exponential. By the way, this is true. This was a study published by some people, and it was paid for by a company that sells wine. And you know what they did? They just said, they took a graph, and it had countries all over the place like this, right? And you know what they did? They said, well, let's ignore all these, and then we get a nice curve that looks good for us. And then we'll say, in a study of like 32 countries, this was the trend we observed. Now, is that true? Well, is it true?
Yes.
Yeah, it's true. It's just misleading. This happens all the time. All the time. And you hear people on TV saying, we have a study that shows this and that. And you got to know that people dig deep. Now, the nice thing is this. No like real scientific journal worth its salt would publish crap like this. But it'll get published somewhere. And then it'll turn up on some news reporter who will go, drinking wine saves your life. Everybody drink tons of wine. And it's like, maybe, but this data sure doesn't show that because it's not honest. It's not complete. If you see a study that shows like 18 countries, you might ask yourself, why 18? Like, and why those 18? Like, is there not something missing here? I mean, if you look here, there's some pretty key countries missing, aren't there? Canada's not on there, but like the US is a big major country. You don't see it on there. Japan's a big major country. Like a lot of the biggest countries in the world aren't on this. Why did they pick the ones they picked? Oh, because it fits the data, right? Now, this is not very good data, but does it make sense to put a parabola through it? No. Does it make sense to put an exponential curve through it? No. Even this one? Is it going like that? Well, that gets pretty weird for that guy, right? So what kind of shape would fit through this? Yeah, it's not great, but I would say the only thing that's going to kind of fit through this is going to be straight line. They added this ruler feature just recently to OneNote, and I'll tell you, I'm a big fan. What do we call this? Yeah, it's a linear relationship. What's this one about? Oh, this is interesting. They measured girls' height at age 2, and they measured their height at age 18. And we discover that, roughly speaking, if you are a tall 2-year-old, you will be, you'll be a tall adult. And if you are, generally speaking, a short 2-year-old, then you will probably be a shorter adult. Now, is that a perfect relationship? No, not really. We've got this person who is a really, really, really tall kid and a relatively average adult, right? We've got this person who is just an average child, right? But very, very, very tall adult. So is it a perfect relationship? No, but it's pretty clear the general direction, yeah? Mm-hmm. Totally true. And this one, this is neat, because I used to do this for a living. So I have a lot of examples like this. This is actually a really interesting one. Temperature versus revenue for an outdoor restaurant in degrees Celsius during the summer. And what we find is, like, if it's chillier, people like to go inside. Also, in the summer, chilly days are often chilly because it's what cools you down on a summer day? Windy or rainy. And are either of those nice if you're in an outdoor restaurant? No. So on really cold days, low revenue. Then what happens? Boom, really nice days, and we sell lots. And then what happens? As it gets really hot, people go, no, I don't want to sit outside. I want to sit inside in the dark with the air conditioning on, right? Does that make sense? Now, what kind of shape fits this model? Annoyingly, I couldn't find a copy of this graph without it already on there. But this is parabolic, right? And if you prefer, you could call that quadratic. It does kind of, it's sort of a deadly sounding word, isn't it? All right, now. So we have 3 basic kinds of relationships we are going to deal with here. But we also have strengths of relationships. Like this here, these are all basically linear relationships. In fact, I made them so that you can draw basically the same line between them. But if I were trying to, make a prediction, which one of these would I feel safe making a prediction based on my line? Yeah, right? Here, basically, you could use that line to make a really strong prediction. By the time we get to here, would you trust a prediction made on that line? Not much at all, right? So it's not enough to say what kind of relationship is there. We also have to ask how strong is that relationship? And we use some really technical language here. We call this a strong relationship, and we call this a weak relationship. And we use a slightly more mathy word here. We say this is moderate. So strong, weak, or moderate. This, by the way, is probably so weak. Like, this is like social science data, because social science research is so messy. Whenever you see these people who study like the effects of like violent television on people's behavior, you see these graphs that just have like dots all over the place, and then they've stuck a line through it. They're like, like the line, a computer came up with it. But, and by the way, this doesn't just apply to lines. Like here, and this is totally true. This is the phases of the moon. No, sorry, not the phases of the moon. This is tidal data. That's right. That's where I found this. So this is how high water is in Cape Breton Island over the course of a day. This is real data. And look how incredibly predictable it is. We know to a very high degree of certainty how high the water is going to go at high tide and how low it's going to go at low tide and how long it's going to take to do it. This is not any of the above. This is actually a totally different kind of relationship called a periodic relationship. Don't worry about it. That's one that repeats over and over again. But is this strong or weak? Yeah, super strong, right? Very predictive. So I could say pretty confidently, hey, 10 hours in, how high is this thing going to be? And you could say, yeah, there it is. We can predict the tides really, really, really well. We can predict like the phases of the moon really well. We know the locations of the planets in the sky really well. Sometimes data is really predictable. Other times, this, oh, what data is this? I grabbed this. I can't remember. But this, we drew a prediction through. How trustworthy is that prediction? I would probably even say weak, right? Like, that is pretty all over the place. I would not trust my life to that interpretation. Does that make sense? All right. Before I leave you alone, I'm going to send you to the rest of this. There's one more thing I want to talk about. All right? And it is the idea of cause and effect. And I found this example last semester, and I really liked it. So this is also real data. This is between the years 1998 and I think 2012. There's not data for every year, but every year we had available data. And we looked at two things in the United States. Well, this is USA, and then this is specific to Kentucky, which is a state in the United States. What two things did we measure? What we got? All right, the marriage rate in Kentucky. So this is per, I want to say, 100 adults. Or no, sorry, this is per 100,000 adults. How many were married per month in a year? So the marriage rate. And this is the total number of deaths from falling out of fishing boats. Somebody has to measure that. There's a guy who has that job. His job is to keep track of how people die, and he writes it down. By the way, when we do a little later in this, we're going to go to the Stats Canada website, and we're going to find all kinds of crazy statistics. Whatever you're interested in. There's some guy in the government of Canada getting paid to keep track of it. So, oh yeah, all kinds of stuff, right? So, all right, well, we'll deal with that here. So now, this is the X, and this is the Y. So down here we have the marriage rate. And up here, oh, I'm wrong. It's 99 to 2010. That's right. And up here we have the deaths. And so this graph shows them year by year, right? And you can see they track each other pretty closely, don't they? So what I did is I took these two graphs and I got the data and I put them into a scatter plot, right? I took the marriage rate and put it on the bottom, and I put the deaths and I put it on the side, and we see a clear trend, don't we? Which is, as more people in Kentucky get married, what happens to the number of people who die from falling out of fishing boats in the entirety of the United States of America? It goes up, right? Right? Like, that's a clear trend. It is clearly going up. Therefore, the only conclusion I can draw is that Kentuckians are getting married, they don't like it, so they're doing more fishing. And obviously, as people fish more, they're more likely to accidentally die by jumping out of the fishing boats. This is to say nothing of the possibility that these women in Kentucky are killing them and then saying, yeah, he went fishing and all we ever found was his boat. Oh, that was incredibly sexist and heteronormative of me, wasn't it? And that's a great discussion all its own. Maybe these women in Kentucky really aren't fond of their marriages and they're going fishing. Or maybe these things have nothing to do with one another. What do you think? I think you're right. Could this be just a complete coincidence? Right? I don't actually have many data points. Could this just be random blind dumb luck? That's right. So if you want to get your safe boating license, the first thing to do is go to Kentucky and break up a lot of relationships. Just break them all up. Yeah, you just got to be like, every time you see a wedding announcement, they do, does anyone have any reason why this couple should not be wed? Be like, I just got my boating license. And I don't want to die. I would propose to you that these two things have nothing to do with each other, even though they graph perfectly onto one another. Just because two things graph together, just because they graph together, it does not mean that they have anything to do with one another. And this leads us to the great fallacy in math and science. And I'm about to teach all y'all some Latin. All right. I'm a big fan of Latin. My wife was a classical linguist before she became a midwife. So she studied all this stuff in university. And so I had to sit through countless hours of listening to her study old Latin texts, and I'm taking it out on all y'all. So here we go. This is the fallacy of post hoc ergo propter hoc. What do we got? Yeah, say it with me now. Post hoc ergo propter hoc. Yeah, you guys suck. Okay, so let's break it down. Because you guys know this. You are better Latin linguists than you give yourself credit for. Let's talk about the word post. Whoa. Whoa, yeah, she's totally right. Think about it. After the football game, what do they have? The post-game show, right? After turkey, what do I get into? My post-turkey sleep. After you graduate, you're a postgraduate, right? So, post means after. Okay? Hoc just means a thing or something. Right? So just ergo, what's ergo mean? This is something that pretentious people mean. Well, give me an example. When might you use it? Based on the last thing. In other words, because of. So after a thing. Actually, I want to change that one. Ergo would be, the best example would just be to say, it's therefore. Like, what it was, it wasn't wrong, but I like that better. It's therefore. Or in other words, in English, we might say, so, right? That's what ergo means. Like, man, I just ate a lot of turkey, so now I need a nap, right? Ergo just means therefore, so. Hence, yeah. Propter means, you could say because of. It literally means a property of. But you could say because of, a result of, and then that thing. All right, so in Latin this means, hey, after something, therefore because of that thing. Right? This is one of the great logical fallacies. I did this, then this happened, therefore. By the way, if you have anyone in your house who loves football, you're used to this. My mother, oh my God. I wore this sweater for the Bills game last week, and they won. Now I have to wear it every Bills game. You're like, yes, Mom. What happened is, way down in Tampa, Florida, somebody caught wind that you were wearing that sweater, and they caught the ball better. You cracked the code, right? But as humans, we love to do this. How many times have somebody said, oh, you just jinxed it, right? No, we all say it, right? We all say it, right? It's just natural. But obviously, if you actually stop and think about it, that's nonsense, right? Like, I get that you're watching figure skating and you go, man, they haven't fallen yet. And then the guy falls and you're like, oh, I jinxed it. But no, you didn't. It's just that people fall a lot in Olympic figure skating. And so after you said that, soon enough, someone's going to fall. But we love to find connections where they don't exist. Yes. Yeah. But this is the ultimate in human nature. We love to find connections where connections don't exist. And it's all fun and games when you're talking about some guy who refuses to watch his gym socks because they won the first game of the season after he forgot to watch his gym socks. Gross, by the way. But, like, it has real problems, all right? It has problems like, seriously, it has problems like celebrities going on TV and saying, I vaccinated my children and then they developed autism. And all of a sudden people don't want to get vaccines for that reason. And that's scary because we all depend not only on vaccines to protect us, but we depend on everyone having them so that for people who can't get them, because they're lethargic, like if we're old and frail, we depend on everyone else being vaccinated, so we aren't moving that disease around. If that starts to fall apart, that's dangerous. It happens when people say things like, oh, we tried this new thing in schools, and that year we had really good scores. So now all of a sudden school boards pour massive amounts of money into doing things this one certain way. And maybe that thing was a good idea. Or maybe we have 20 kids in a grade 9 group, and this was a strong group, and last year's was a group that struggled more, because kids are different. So maybe what we did made the difference. Maybe the kids made the difference. You can't just assume that we did something so it mattered. Just like you could say, like, oh man, we hired this new teacher and the grades went way up. He must be amazing. Or oh, we hired this new teacher and then we had a really bad year. He must be terrible. There's more to it than that, right? But we love naturally to see connections. We are all guilty of the fallacy of post hoc ergo propter. They call it post hoc fallacy. And it's something we have to watch out for. Just because we had a few years where lots of people got married and lots of people died, and then we had some years where less people got married and less people died, and I tell you what I think's going on. We know that in general, marriage rates are going down because kind of our view of public morality has changed. It used to be the case that people kind of thought, if you're going to be in a long-term relationship with somebody, you have to get married. And now more and more people think you don't necessarily have to get married. And so, in general, marriage rates are going down. Lots of people still get married. My wife and I got married, but lots of people also don't. So that's the general trend. What about votes? Well, in 1999, I knew one guy who had a cell phone, and it looked like the Zach Morris phone. It was like the size of your skull. And by the year 2010, just about everyone I know had a cell phone. Could that have something to do with voting accidents killing fewer people? I think so, right? If you're stranded on a boat, but now you have a machine that can tell you exactly where you are and phone people, yeah, that might keep you safer, right? So these two things may have nothing to do with one another, and there's a perfectly reasonable explanation for why they have similar trends, right? But we naturally want to commit the error of the post hoc ergo propter hoc. We naturally want to assume there's a connection where one doesn't exist. We've got to be real careful of that. And I'm going to try and throw, once we get up to the computer lab and doing some real research, some cases where you really have to ask the question, are these things really related, or are they just coincidence? All right? So we insist that we only say one thing causes another. If we can suggest, or if we can explain how and why that might be true. So unless we have some explanation, not just for the fact that these two things move together, but how they move together, how it happens, why, what's actually happening that these two things might be related. If we can't do that, and if that's not plausible, then we can't say they cost each other. Otherwise, we're committing the post hoc fallacy. All right, and we should test the difference. So I'm going to leave it there. I want you to go back and work through those questions, and I also left you with this practice, which this comes from a real chemistry lab I had to do in my second year at university, where we had to take some caffeine and put it in water and then measure it with a machine to see what reading it gave us on the machine. And then we had to take a bunch of beverages and see what measurement they gave us on the machine. And from that, we had to figure out how much caffeine was in the beverage. Kind of a cool lab. So you guys are going to recreate my data, and I even made like a nice pre-made graph with scales for you. You can tell me what you think. And we're going to talk about that on Monday. So there you go. So work through that. You got about 12 minutes left. That's time to get lots of this stuff done, and we'll carry on Monday. Yes, ma'am. Of course, yeah.